Have you ever wondered how these massive AI models actually get trained? I mean, we're talking about models that are so unbelievably huge, they can't possibly fit on one computer. It's a fascinating problem, right? Today, we're going to pull back the curtain and see how you teach a true AI giant. So, just to wrap your head around the kind of scale we're talking about, look at this number. That's 1.76 trillion. That's how many parameters or tiny tunable knobs are inside just one of these big models. Trillion. So that brings up a pretty big question, right? How on earth do you coordinate that many moving parts when they're spread across sometimes thousands of different processors? Well, believe it or not, there's a system to the madness. Let's dive in. Okay, so first things first, let's really define the problem we're up against, the giant model problem. It all starts with the hardware, the very engines of AI, the GPUs. And even the most powerful GPUs in the world have some hard limits. You see, it's just a raw space problem. The model itself, all those parameters, plus the data it's learning from and all the math in between, it's just too much stuff to cram into one GPU's memory. So the obvious answer is, okay, let's just use a whole bunch of GPUs. But that's when you run into an even trickier problem. And this is where we meet the real villain of our story, the communication bottleneck. It turns out the biggest challenge isn't raw computing power. We've got plenty of that. No, the problem is getting all these GPUs to talk to each other fast enough. It's basically a giant traffic jam. And this just shows you the huge gap we're talking about. A GPU can crunch numbers at the speed of a rocket, but sending that information over to the GPU next to it, that feels more like snail mail. And the name of the game in training these models is to keep those GPUs busy computing, not just sitting around waiting for data to show up. And here's why that happens. It's all about distance. Data moving around inside the chip itself, super fast. Moving it to another GPU in the same box, a bit slower. And sending it to a GPU in a totally different machine across the network, oh yeah, that's the slowest by far. So engineers have to become masters of choreography, planning every move to avoid those long-distance trips. So how do you manage all that complex choreography? Well, you need a shared language. You need a set of pre-planned moves that every single GPU knows how to execute flawlessly. You can almost think of them like plays in a football team's playbook. In the world of high-performance computing, these plays are called collective operations. They are these beautifully optimized tried-and-true patterns for shuffling data around. They're built into software libraries like NVIDIA's NCCL. So instead of telling each GPU what to do individually, you just call out the name of the play, and the library makes sure everybody executes it perfectly. Now, the most important play in the entire book is called all reduce. Let's walk through it. So imagine every GPU has just done a calculation and figured out its own little piece of the puzzle, a small correction for the model called a gradient. The first part of the play is reduce. All those individual pieces get sent to a central spot and combined, usually averaged out, to create one unified update. But that's only half the story. Once you have that one, final, averaged result, the second step kicks in, broadcast. That single number gets sent back out to every single GPU. And just like that, after one all-reduce operation, every GPU is working with the exact same up-to-date information. Everybody is perfectly in sync. So now that we have our playbook, right, we know the moves, we can talk about the actual game plans. There are three main strategies that engineers use to split up this massive job of training an AI model. First up, we've got the one you'll see most often. It's the most straightforward, and it's called data parallelism. And, the name kind of gives it away. It's all about the data. The way this works is actually pretty brilliant in its simplicity. You give every single GPU a complete identical copy of the AI model. Then you take your giant data set, chop it up into little pieces, and you give each GPU its own little chunk to work on. They all process their data at the same time, and at the end of each step, they use that all-reduce play we just learned to average their results and update their models together. Yeah, the easiest way to remember this is it's the same model, just working on different data. It's like having 100 identical factories making the same thing, but each factory gets its own batch of raw materials. It's a fantastic way to speed things up. But what if the factory itself is just too big to fit on a single GPU? Well, that brings us to our second strategy, tensor parallelism. Now, a tensor is just a fancy word for the big grids of numbers that make up the layers of a model. And you use this strategy when those layers are just too wide for one GPU to handle. So here,
Instead of splitting up the data, we split up the model itself. Each GPU holds just a vertical slice of every layer. They all work on the exact same data at the same time, but each one only does a piece of the math. Now, this means they have to be talking to each other constantly, sharing their intermediate results to piece together the final answer. And for that, you need seriously fast connections between the GPUs.
So you see the difference? It's a total flip. If data parallelism is a bunch of identical factories, tensor parallelism is one giant factory, where each worker is just doing one small part of the job on a single item. All right, strategy number 3 is pipeline parallelism. So we've split the data, we've split the model's width, but what do you do when a model is just insanely deep? I mean, with hundreds and hundreds of layers all stacked on top of each other? This is where the assembly line comes in. You chop up the model horizontally. The first GPU gets the first few layers, the second GPU gets the next set of layers, and on down the line. Data comes in, gets processed by the first GPU, and the output gets passed to the next one. The trick here is to break the data into tiny micro batches, so there's a constant flow, making sure no GPU is just sitting there with nothing to do.
And that's really the perfect way to think about it. It is literally a digital assembly line, where each GPU is a station that's responsible for one part of the process.
Okay, so let's just quickly recap the 3 game plans. Data parallelism slices up the data. Tensor parallelism slices up the model's width. And pipeline parallelism slices up its depth. But here's the real pro tip. In the real world, you don't just pick one. Engineers create these sophisticated hybrid approaches, mixing and matching all 3 strategies to perfectly fit the unique architecture of their model and the hardware they're running on. So when you step back and look at the whole picture, it's not just a bunch of technical tricks. It's this beautiful, incredibly complex dance, a performance where thousands of processors execute this perfectly synchronized choreography of computation and communication. And really, what we're learning to do here is not just train AI. We're learning how to solve problems that are way too big for any single mind or any single machine to tackle alone. It's a fundamental lesson in collaboration at a massive scale. And that really gets you thinking, doesn't it? As we get better and better at orchestrating these digital symphonies, what other challenges that we think are impossible today might actually be within our reach tomorrow? Thanks for tuning in.